Okay, for those who don't know me, I'm Marc. I hack on KVM. For those of you know me, well, you know me. So it's going to be rather technical, and it's going to be extremely arm64 specific. If I lose you at any point, shout at me, say I don't understand. Equally, come to see me at the end of the presentation, and I'm happy to explain anything, if I can. So, once upon a time, a long time ago, someone invented nested vert on ARM, and the first version, although it was very simple and really nice, it was a real disaster performance-wise. Really didn't work. About a year later, we got NV2, NV again, really more complicated, but really with a potential for much better performance. Came with its own set of problems. Including some things that do not virtualize at all, but okay. So early work by Jintak and Christopher over there. We prototyped the whole thing, including bits of the architecture that would become eventually NV2. After, between 2017 and 2019, a bit of work, but nothing fantastic. Became mostly a hobby after 2019 until 2022, where I got hardware, this very machine here. And yeah, it's in, finally, after 9 years. So we support Fit and V2, we support VHE and NVHE guest independently, you can't have both. Recursive nested on VHE guest. There's hardly anything left from the original code, apart from the stage-to-page table walker. Thanks, Christopher, again. And yes, thanks to all these people who really, really helped me building this, including, yes, some really annoying emails saying, oh, yeah, but nested vert is a solved problem. Yes. So what took us so long? Well, let's take a step back. What is it to virtualize EL1? For those who don't know how ARM works, there's EL0 user space, EL1 kernel, EL2 hypervisor. After that, it's firmware. So virtualizing EL1 is interesting in the sense that the virtualization extension on ARM basically ignored all the Popek and Goldberg paper and all those principles to invent something different. Well, a bit like Intel did, something different. So a new privilege exception level, EL2, that gives you just enough primitives to virtualize EL0 and EL1 relatively easily. You can easily virtualize the CPU because you can save, restore everything. You can virtualize memory because you have a second stage of translation. You can sort of virtualize time by offsetting it. And you can sort of virtualize interrupts. And those of you who followed the VGeek adventure know what I'm talking about. So that's actually pretty efficient. So if you're not, too difficult, you can write your own little pseudo hypervisor in a matter of hours. It's not that hard. Of course, if you're not too picky about implementing actually the architecture. And for KVM, most of the complexity, I say here 90%, comes from being integrated with Linux because pages are being taken away from you, you get preemption, all these nice things. And of course, the other 90%, that's virtualizing interrupts, as everybody knows. So virtualizing EL2, so even if we had some really good basis to virtualize EL1, well, that doesn't really transpose with EL2 because if you wanted to adopt the same method, then yeah, you need an EL 2.1 and EL 2.2 and ad nauseam. You can't do that. So actually, Popek and Goldberg, maybe they had a clue, maybe. So the only possibility to actually make EL2 virtualizable is to allow it to run at the same exception level as the virtualization we already have, virtualizing EL1. So we have to be able to deprivilege it, pretend that it has access to some registers it doesn't really have access to, and either have shadow registers or be able to do trap and emulation. So effectively, the virtualized EL2 runs at EL1, so that flattens the virtualization stack. So can think of EL2 and EL1 as some sort of KVMs, which really mimic the plane concept. And the only difference with the plane is that actually there are actual rules on how you transition between these two planes. That's the architecture. But that means that to do that, we need to virtualize all these goodies that EL1 virtualization gave us. And that's basically writing a CPU in software. It's not exactly simple. I started that, I thought, yeah, it's going to be easy. Not at all. So everything that we take for granted when virtualizing EL1, well, we have to implement it in software. So we have shadow page tables. We have to do all kind of TLB management. We have to implement page table workers to do address translation. We have to emulate some instructions. Timers must be multiplexed. And the trap routing is quite complicated. Not everything can be virtualized. That's mostly outlined some issues with the base architecture. And actually, the easiest part of it all was to virtualize in Trust because we had already done all the hard work. Virtualizing Gig V3 is 200 lines of code. It's almost trivial. But that brings us to some other thing. Is that CPU features, that's really a central thing in ARM. Everything that, any characteristic that your CPU has is a CPU feature. So what's in a CPU feature? We get a set of, not all the time, but including instructions. We get new registers, or we get new register fields. We get traps, we get exceptions, we get some defined behaviors. And that's fine. But what does it mean to not expose such a feature? It means that these new instructions, they must undef. These system registers must undef as well. When I say undef, generate an undefined exception, something that the CPU says, I don't know what you're talking about. Register fields must have reserved behaviors, and I'm going to touch on that the next slide. If you have trap configuration, they must not take any effect. And the exceptions that your magic feature foo would normally trigger, well, they must not get triggered. And all that, at least in KVM, we control it with a single feature field in an ID register. That's architected. So what are these reserved values? ARM has res0 and res1 as basic definitions. And what it means is that this bit is reserved, and it either has a value 0 or a value 1. It's a bit. Yeah, so far, so good. But the definition of res x is a bit complicated. So it's either the value is x at all times, means that the bit is not stateful. It has always that value. You can write anything you want to it. It will always have that at the value that has been specified. Or, alternatively, it can be read as written. You can write any value you want, being 0 or 1. I have no choice. But it's always interpreted as x. And that's if your register is stateful. But also, if you have what we call an indirect write, which is effectively the CPU itself generating that value, or in our case, KVM generating that value in a register, the value must be x. These are the basics. So it's a bit cumbersome, and people at ARM spend a lot of time bickering about what that actually means when implementing bits and pieces, but for what we are concerned about, these 3 points are just enough. So NV2 has an interesting behavior in the sense that registers, or what looks like registers to the guest, in a number of cases are actually backed by memory. And it's just normal memory. The hypervisor has allocated a page, and the guest, on doing a system register access, unknowingly writes to memory, for example. The problem is that these writes are completely unsanitized. You can write any value you want. They are all valid. They're not necessarily valid from an architectural perspective, but from the point of view of the guest, it's a free-for-all. So it means that KVM A must not be tricked into assuming that value X means that feature, the feature that is controlled by this value has to be honored if the feature is not implemented. You have some citation here. You must have consistent behavior across registers that are part of the same feature, and preferably you write all that without ending up having all sorts of tests for all possible features everywhere in the code. So what we do for that is that we compute these reserve bits when the VM gets initialized, and then we hack all the system register accesses to actually sanitize these registers as KVM uses them. So that complies with the REST-X definition in the sense that bits are read as written, but also if KVM writes to that, then we enforce the value X in that system register. And that avoids all sorts of checks in the code. But that's only one thing. And then that links to other things, and especially things that Cornelia and Sebastian have been working on, is that for a very long time, KVM, and until now, since the set of features exposed to a guest has always been that of the host. I mean, for a very long time, we couldn't effectively distinguish the two. We didn't have the infrastructure for that, which means you could only migrate between two identical machines, or very close. Well, there's been some effort to break apart what is a host feature and what is a guest feature, so that user space can actually choose what it exposes to the guest within the limit of what the host has. But that's also more or less required to enable NV in a gradual way. We wouldn't be possible to enable everything in one go. Just we don't have the manpower of that. So we start by trapping all the ID registers. We sanitize that to expose only the feature we have. We try really hard to hide unimplemented instructions by using traps and injecting undef back into the guest. And also we decouple the view that KVM has of the reserve bits from what the host sees. Because it's quite common that someone will add a feature in Linux, support for a hardware feature in Linux, but not enable it for KVM. If we took the view that everything that the kernel knows, KVM knows, we could end up with trapping things that what we're not supposed to trap, or let the guest deal with state we're not supposed to expose it. So we split these things in a sort of nice way. But how we end up dealing with that? So effectively, we'd like to implement something that looks like this. So if you start from the middle of the picture, it took me ages to build this. I don't know why. If you start in the middle of the picture, you have the guest feature set. And so that populates the ID register. The ID registers themselves are able to impose some limits on what is exposed to the guest. From the ID register, we want to actually derive the reserve bits that constrain the guest control traps, but that also generate host traps so that we can actually make things undef. And you take those two sets of traps, you combine them, that gives you your exception routing, and then you can use that to enforce instruction and register undef. And yeah, if you think that hurts, yes, it does. It's extremely painful. So how do we go about building this, or something that looks like it? The saving grace is that we don't have to actually implement it by hand. So ARM has released a this thing called the ARM Architecture Machine Readable Specification, ARMRS. It's a bit of a mouthful. And it comes in two flavors. There's, on one side, a huge number of XML files and HTML files, and it has the full architecture definition. It has everything you can want to know about the architecture. It's actually how the ARM is more or less generated. All the registers, all the instruction, the pseudocode, the description. But it really is under a very difficult license if what you want to do is open source software. Additionally, and more recently, ARM releases 3 enormous JSON files that contain instruction, register, and feature descriptions, plus some schemas, and it's quite big. It's about 100 meg. It's labeled as open source machine readable data. So it's much more basic. It lacks, it has none of the text. It has no shared pseudocode, but has just enough data to build what we want to achieve. And more importantly, it's BSD licensed. I left the link where you can actually download the latest. So how do we make use of this? Well, first, it comes with all the system registers with the encoding, all the fields. It contains all the dependencies on features on the fields and on the ID registers. Describe all the traps and the routing of these traps. So it's relatively easy, even for someone like me, to write parsers for that data and extract bits and pieces. So you can dump most of the data relevant to system registers. You can find what register is tracked by what control bit. You can find how a feature is advertised to a guest or to software in general. And yeah, I have some tooling on this Git tree. Also import the archMRS itself so that I can do diffs between architecture revisions. It's quite interesting sometimes. I need to speed up. So that's what it looks like with one of my little scripts. So HCRX-CR2 is one of these control registers for the hypervisor. And you see that all the fields are detailed, but also we get all the conditions for which these fields are valid. And we're really interested in that. So to give you an example, this is what we had just to compute the res 0 bits before we started using that. Don't bother reading. The font is small on purpose. But yeah, it's not very nice. And we move to this, which is a bit better. And not better because it's shorter, but because it's entirely generated. No code has been written by hand. I wrote a bit of awk and bash, taking the initial dump and placing the fields where they should be. Of course, behind that, there's code actually parsing these tables, but that code doesn't need to know what register it's dealing with. It means we can also do other things. Is that, for example, we have these registers called fine-grained traps, which you get one trap bit almost per system register. And it's quite nice, and nested vert makes heavy use of this. So once we have that description, well, we can, of course, enforce the reserved behavior when features are not available. But we can also automatically generate trap configurations so that we can enforce that if the guest uses the corresponding system register, despite that register not being advertised, we'll take the trap and we can inject an undef. And that allows us to build an infrastructure that tracks for any given system register, for any given trap that affects it, whether that register should be either handled in the L0 hypervisor or redirected to the L1 guest, or alternatively injected as an undef in the L1 guest. And that happens independently of nested vertices. Now, an infrastructure that we have for KVM in general, or KVM arm. And that removes a lot of complexity when you have to write these things. You just dump the data and you let the generic code make use of it. And how do you write these trap routings? Well, so for example, here's our friend HTRX at the top. And we're looking for what controls, what registers that this control bit, SCTLR2EN, what registers it affects. And then, yes, we see a bunch of existing registers with their encoding and some conditions. And we know that, yeah, if the bit is 0, then things trap. And that actually condenses into this single line, SR trap, SCTLR2EL1, with a bunch of additional conditions, because there's not just a single bit that traps these things. Similarly, for the fine-grained trap I was talking about earlier, we can work out, okay, what does the bit SCTLR-EL1 in HFGR-TR-EL2 traps? Well, it traps not just SCTLR-EL1, but also SCTLR2-EL1 and EL2 with nested vert. So that we convert that to these two lines. And we have about, 1,200 such lines for each system register. So we have a lot of system registers. But it means that we can build these things in a completely, almost, I wouldn't say automated, but without having to think too much about it. Because once you start having manual interventions, you'll introduce bugs. That's pretty. So if we go back to my original little scribble, that's where things happen. So the only 2 bits where we still have actual code manipulating that data, or the actual content of the registers, are in the ID reg code on the right side, where we still have some limitation where we have to express, okay, you can't go past that hard limit because we don't have the emulation code for it. For example, our PMU management code is capped at 8.4. We don't go beyond that for now. And on the other side of the spectrum is our entry code, because we effectively combine trap controls coming from the host and from the guest. Though there's a few things where there are some bits that we don't want to leak from the guest into the host, and that's still a manual process. I don't have a good idea on how to automate it, but still thinking. So overall, we got rid of a lot of code. In terms of volume, it's far worse because we have huge static tables. But again, they are mostly generated. So that's been yet another big pile of free work. And with that, I'm still not even a third of Sean. I'm really pissed off. So we automatically generate our res bits. We trap to undef. All that is validated at boot time. So if we are missing bits, if we have overlapping descriptions, if anything is not quite where it should be, we scream. I wanted build time checks, but I've been told not to. That has allowed us to consolidate all our trap routing into a single place. So it's just one lookup in a big X array, and that returns a 63-bit word containing all our routing information. And that's completely static. It's become quite easy to spot patterns, common patterns, optimize for them, but also work out when the architecture doesn't virtualize. Again, if you see a control bit in a register that is solely written to memory and that has impact on something that doesn't get trapped, you know that feature doesn't virtualize. And you remove it from the list of features you want to support. So it's really an improvement to the maintainability of the code. And one of the things I use a lot is to be able to diff two versions of the architecture. It's quite enlightening sometimes to see, that thing has changed. There's been a fix in the architecture. How do I reflect that into the KVM code? And you can actually regenerate your tables and compare what has changed. And yeah, we shouldn't copy anything from the ARM anymore as much as possible. And yeah, if you're doing it by hand, you're probably doing it wrong. That's been my take on this. So what it means for people actually hacking on KVM. So if you have new fields, there's this arm64 wide file sysreg where you can put the register description, you auto-generate it, you dump it there, job done. Conditional fields, they're in config.c, and that's what generates a lot of the enforcement on the rest of the configuration. Trap routing in the really badly named emulate nested, which is really not about emulating nested anymore. And as usual, if you have to handle a trap, it's still in sysreg.c. That hasn't changed. We really want to see unsupported features described in these tables. Don't leave anything out. It's important that we see that we have the code that will, at least the description of the feature. Thankfully, because we have the full description, we can blat the rest, the bits out, and the feature will be disabled when the feature is disabled. If you have to check for features, we have this condition, this predicate that KVM has feet, dump a feature name, and it will do the right thing. We don't, nested support is now not optional anymore. If you come up with a new architectural feature, please add support for nested. We don't want nested to lag behind other things. There's still some work to do in terms of register sanitization. So not all the registers have been gone through this treatment. And the tooling is really bad. I can't write GQ scripts at all. I mean, I've hacked things together, but I feel like I'm writing Lisp, so must be doing something really wrong. And Joey Goulet is working on an automated test generator on this, using the same stuff. So yeah, it's been an interesting journey. It has impacted all subsystems in the hypervisor, and nothing's been untouched. But it has introduced new ways to handle the guest feature set, and it's probably enabled ways to ensure that we deviate less from the architecture. So is it the last time we rewrite everything? Probably not, but as far as I'm concerned, yeah, it's probably the last time I do it. I've had enough. That's it. Thank you.